First of all, I'm very thankful for invitation. It's very, very pleasant for me to have this opportunity to talk. I use this also on this occasion to revisit some earlier involvements in topos theory that I have been away from for several years. But actually, like more or less around 15 years ago, like my first ever like scientific talk that was kind of meaningful in a scientific sense was actually about like topos models of synthetic differential geometry. So kind of it's very nice for me also to come back to those topics. So, and I'm also like, before I will start talking about what I'm talking, I also want to say that it's very hard for me to get out of the mathematical physics ghetto, so which means that there might be too many symbols on the slides, and don't feel like embarrassed by it. I will try to not be embarrassed by myself. It's just, you know, it's like letters sometimes like to have like domains and codomains, and I'm trying to kind of be exact when I can, but it makes things like not very readable sometimes. So like I will try to convey like main message, like more like a water in between like those stones of mathematics. So, okay, so let me start what I want to speak of. So basically, Jane's on the side of like people involved in probability theory and also in physics, and Hintika on the side of like people doing formal logic. They have both, in their own way, were very stressing the distinction between two different layers of understanding of logic, or like for Hintika, it was more about semantics and like revisiting also Tarski and like early 20th century program of logicization. In case of James, it was more about like actually the structure of physical theories and also the foundations of probability theory and statistical inference. But in both cases, like somehow one can turn to that like when we speak with logical inference, there is actually like, in a broad sense, there are actually like two different meanings that one can apply to such a term. The deductive inference, it's something that we usually have in mind when we speak about logic, and it's like first order logic, quantum logic, Haydn algebras, inner higher order type theory in toposes, and so on and so on, or like Martin Luft type theories associated to groupoids or something. Like there is like, you know, an infinite chain of possibilities, and basically like the sort of, it's not really a definition what I'm saying, but like the intuition is that like one can deduce formulas from true valued, or in another way sense, like certain presumptions. You can build up formulas, and then you can derive some conclusions that are also completely valid and certain, given the certainty associated to the symbols from which you were like concluding your inference from. And in case of inductive inference, such like basically any form of statistical inference, and like the rudimentary version of it, like known already in like which is like 17 something, it's like 18th century, yes, it's like 20th, yeah. So like in 18th century, you already know like Bayes Laplace rule, yeah, you have some sort of certain things that you know, but actually this what you infer is something that holds with certain plausibility, or with certain degree of certainty that is not certain, in the sense that, for example, like if you can try to formalize in terms of generalized true values and so on, there is still the way you use this logic, the epistemological layer of it, that will somehow defy this type of formalization and this like this attitude to formalization that's applied to deductive inference systems. So this is some sort of like distinction. And now if one like, for someone who is like, has been accustomed with Lavier approach to categorical logic and like generally foundations, like categorical approaches to foundations of mathematics, let's say, and also like the structure of toposes, there is like this question like whether this perspective on like logic can be injected to, or whether it should be considered in the mathematical structures of category theory, when one tries to use those structures for physical theories, in the sense that, like, you know, physical theories is actually, I mean, you know, we actually like take some data, it's like some numbers basically, or like some even non-quantitative things, and this is always like some finite collection of data points. And, you know, like if you have finite collection of data points, you can like draw infinite number of different functions in between. So like in principle, like physical theories is something that it's not something that is you know, absolute in a sense. There is always some sort of like principles of inference that guide you, that you choose this function, not the other function, that you kind of, it's not kind of like when people speak of like ontology of physics or something, there's like always when one asks how this or the other theories apply to data, there's always some sort of like uncertainty issue that is dealt with, and this is where inductive inference comes in. And I think that like, so like the basic intention is like to look at physical theories from the scope of view of some categorical developments and see whether this inductive inferential layer can be somehow discovered or injected or like observed, that it's somewhere out there, in the sense that like with the main guiding idea that in shift, it's a quote, I don't remember from who this quote is, it's just like in the back of my head, and Google gave no like direct answer. I think maybe it's a gray volume on like toposes from late 70s, introduction or something, but basically it's like a phrase that like I remember like read many years ago, and somehow like, you know, in shift theory you really have like algebra vertically, topology horizontally, but if you think that there is some sort of algebra logic duality, and on the other hand you have like topology logic duality, like maybe it's actually a place where this distinction between two different logics could be investigated or injected, or it's you know, it's a preliminary suggestion. Okay, so first thing I would talk about it's some sort of relationships between toposes and general relativity. So probably there is like a strong division line between people here who know what topos is and people who don't know what topos is, and I think it's like it's impossible to explain this exactly by now. But basically, like if you think there is, I will give you some intuition about this about it. So like if you take any category, and there were like categories were appearing here already several times, and then you consider like set of all, okay, set, like if you consider a category of all functors from this basic category C to sets, then this functor category is like a rudimentary example of topos, and then you can, for example, you can introduce some sort of notion of generalized covering families of this category C. There's some definition of this. It's called the Grothendieck topology, and you can, for example, select only those functors that are they behave like generalized shifts with respect to this generalized topology, and a result, this process is actually functorial, and the result is called a Grothendieck topos. And this is like more advanced version of what topos is, and there is like the final version, which is actually like you take purely categorical definition of it. It's category that has all limits, exponential, and sub-object classifier, but this already requires some sort of like a special you know, work to be done to actually understand what the definition means. But it doesn't matter so much. The important thing is that like topos provides a universe in which can be considered as a model of higher order intuitionistic type theory. And this subject classifier in particular, it's like it's a Hating algebra structure in which which effectively gives you something like a naive set theory without the law of excluded middle. So you can prove various theorems provided that you don't use law of excluded middle, and like various things associated with it, yeah, like an axiom of choice. This is like, so already here there is some sort of like distinction between the layers of abstraction. One thing is that like one can take this type theory, and like with any type theory, one can try to write some formal structures like algebraic structures, geometric structures, and so on inside this type theory, and use the power of this type theory to kind of prove some theorems. But then if it gets represented as a topos, there is a question, okay, like if this topos on its own are just some functors over some basic category, what is the meaning of those particular objects of this base category, like for those synthetic formulas? So somehow like there is, I kind of try to avoid everywhere saying ontic, in the sense that like I actually mean structural. I don't want to identify structural with ontic. I will return to, or at least will try to return to the later to the explanation why it is so. But you know, like one thing is formulas, and like formulas don't carry with themselves like ontic burden. Actually, like logical positivism was to some extent about it. So and then there is like some sort of topologization extra that provides some sort of extra intent. And now, following this original line, okay, but maybe in a moment. So the main message, like already in the setting, is that like you can basically take anything from this base category and consider this as a functor, so like an element of the topos. It's called Yoneda lemma. It's like this, like a principal tool, and like I would say like first insight in all theory. And so, for example, like if you have such a type theoretic formula of sort of like if someone is like hardcore logician, I'm merging few terms here, but it's impossible otherwise to speak, you know, with enough speed. But basically, it's some sort of like knife set theory that there is some sort of dependence of the belonging of an element to a set, and this gets like proper formalization, this higher order intuitionistic type theory, and basically like in topos it gets modeled that we think of like an generalized element of a set as actually, when looked externally, as the element of the set of all maps from between the underlying objects. So it's some sort of this Yoneda lemma gives like sort of way of translating between like what happens inside and what is like synthetically described by the means of this type theory, and external view when you deal with presheaves or sheaves over the base category. Okay, so now now it's like, okay, this is nice, but so what? And the like in order to get to any sort of physics, we need to have some sort of more structure, and like in order to have like GR, we need to have some differential geometry at least. So the step for it is actually like there is a system of differential geometry that was developed precisely as a development designed for toposes. It started from Lavier's talk in 1967, categorical dynamics. It was much like just some sort of phrases that seemed to be nice, and then people put like hardcore work in 10 to 15 years they developed like full-fledged theory. And basically this thing is that you take particular class of toposes. So I think that already like in several talks here, like people had this sort of discussion of relationship between algebra and geometry by means of spectral duality. At least for commutative algebras, this goes back to Stone-Tarski representation of Boolean algebras as sets, and then like hating algebras as topological spaces. And on the other hand, we have Pontryagin duality for groups and Gelfand representation for commutative sister algebras. And you know, there is like a bunch of dualities. One can organize them, find dualities between dualities, and so on. But basically, like this is another case of the same story. We can think of smooth functions over smooth manifolds as commutative rings, and think of representation of it, think that manifolds are representations of those rings of smooth functions. And again, like, so this is nice, it's cool, but the trouble is that like it doesn't give everything what we would like to have from the manifolds. And in particular, one of the things is that like the category of manifolds, and like the same for its dual, it's not Cartesian closed. So Cartesian closure like basically boils down to the fact that if you have like a space and you have like other space and you have like OR all maps between those two spaces, you want to have the space of those maps also to belong to the category of those spaces. And it's not so for smooth manifolds. However, immediately already from Yoneda, it follows that if you just build up presheaves over C-infinity rings, you get Cartesian closure. So somehow like already like this shift from like basic category to presheaves over category like makes semantics available. So like in the background you can say like synthetic type theory that corresponds to it like stronger, well weaker, like technically weaker, but like stronger in the sense how much can be expressed. Okay. And also other thing is for people who know what jets and germs are, you will know in a moment, but like for those, it's like there's like no representability of jet functors. But the other motivation is second of this is like model motivation, but there's also synthetic motivation, is that there's like long story whether infinitesimals make sense as objects. And the thing is that basically they don't if you use Boolean logic. Because like with the exclusion law, like the principle of excluded middle, you cannot have things that are not 0 and square to 0. However, you can have it when you just avoid law of excluded middle, and that's the point. You just start from proving things in terms of Heyting algebra, and then you can just start from the postulate that every function is like the first order Taylor expansion in terms of differentials. Sorry, in terms of infinitesimals. And what you do is that then you just start from like some commutative unital ring. You don't say that this is like a ring of smooth function, nothing like that. You just say it's like an abstract ring. You say that it has some subset, or like it's actually like subtype, but I'm using like naive set theory by now. And then, like with this axiom, there is some sort of nice thing that actually, like, there is some sort of like there is like an infinitesimal line everywhere in every function, and it's still like the function will be still smooth. So it's kind of cute. So then this gives like only infinitesimals in order to have like representability of all jets to like get all those differential geometry going. We need to get like higher order jets, and then it's like Coq-Lavier axiom gets generalized to basically like securing that that it holds for all spectra, also called Weyl algebras. I will not go into details, but basically just think of it that there are some algebras that encode all these algebraic properties of infinitesimals that we would like to have to prove various theorems in differential geometry. You know, like in differential geometry, when people prove things in like using coordinates or like using some other stuff, there is, you know, all those things are irrelevant. Like results are expected to not depend on coordinates or something, or like, you know, all to free things, and this basically formalizes this like algebraically. And okay, and at the end you get some zoo of various infinitesimal objects, and the nice thing here that I just want to notice is that there are like various spaces of jets, and then like there are some sort of like, this is like symbolic thing for like the space of all jets, all diagrams, all Weyl algebras. But the nice thing is that actually like you can have also, at least synthetically by now, you can have like larger space in which you have all non-invertible infinitesimals, and which is the same as such x's that double negation is equal to 0. So it's kind of, it's precisely like this would be 0 if we would have excluded middle, but excluded middle is precisely equivalent with double negation not equal to truth. So like by this sense, like this is an exploit. It's like, I mean, Boolean wise, it's an exploit. You just break down the system and you have like all infinitesimals like in the point. But there is also like a bit larger space, even so, defined like this, defined arithmetically. I would like to notice it. And this space is basically the same as the former, in many models, except of the models which use forcing. And then in this larger space, there are Robinson non-standard infinitesimals also. I kind of write them here-ish, synthetically, not forcing-wise. And it's kind of funny that like all those like double negation, all those like algebraic sort of, so basically those guys are germs. This is like when it gets to representation, this object turns to be a sheaf of germ of functions. Yeah.
Big cup should be big cap. I mean, this should be intersection, right? This fuzzy delta.
Yeah, it's very possible. I was changing symbols in last moment. Let me say, I mean, definitely there should be some sort of where? Here?
Oh, yeah, this should be intersection, right? Above.
Here. This one. Yeah, I suppose. Let me see. Yeah, precisely. Yeah, totally. I mean, the coherence of those three formulas requires this to be inverted. So actually, like, we have two sad faces, not one happy. Okay, anyways, let's go further. So the thing is that, like, okay, all this stuff gets represented and like in those toposes, so like first we had like all this was like synthetic theory. Yeah, just formal theory in type theory, it's going on. Here it gets represented by functors. Now all those symbols of the language become functors over the category of C-infinity rings. Yeah, so yeah, I'm just saying this, but this is Yoneda because in all those toposes that are well-adapted models, they are designed in a way that Grothendieck topologies that are chosen, there are so-called subcanonical, which basically means that Yoneda is still full and faithful. So like basically like whatever is a sheaf is still like, I mean all sheaves are sheaves sort of. So, I mean, okay, no, but Yoneda is full and faithful still. So, okay, and now what I want to tell you, yeah, basically I told you this, what I told you, but the main thing is that like there are like different models which are imposed precisely by making, constructed like from, you start from like this topos, just presheaves over C-infinity rings, which is already Cartesian closed, and then you sheafify it, how to say it? Sheafify, yeah, you sheafify it into the more stronger toposes, and like differently on the choice of sheafification, you actually have a representability of different objects inside. So like coming back to this story with this, you know, like topology horizontally, algebra vertically, the thing is that somehow like, for example, gem representability gives you existence of unique solutions of partial differential equations. And without this, you don't have it. Without this, you only have like infinite jets are just like formulas of PDEs. You actually don't have solutions. You actually like there is no epistemic meaning to partial differential equation without like actually specifying what is the solution uniquely. It's just a formula that you can, you know, draw on the walls, not of this building because it's nice, but like somewhere, yeah, on the Berlin Wall, for example. And I guess no one did it, but the thing is that somehow, effectively, this what you get is somehow like that for free by this topos architecture, and for free you get only the algebraic structure to work to get like actually the solutions, and also like there is some details in like Mordai Krayu's book, but if you dig into it, you will see that actually like the choice of specific class of solutions of PDEs also can be controlled by means of choice of particular Grothendieck topology and also forcing. So it's kind of interesting that like you can, and you know, like actually like existence of this or other solutions is this epistemic part. Yeah, you can say, oh, like, I mean, if you write me like, you know, PDE in like on the next page, it would be like Einstein equations, you write me PDE, like it doesn't tell me like where I am, you know, I mean, it doesn't fit any points, it's just an equation. So this is like one message. Okay, now this hour thing is so great, it's kind of, I actually may make it. So I will definitely make something and call it the day, you know. So and anyway, like let's get to this. So I will tell you like supernatural thing again, like I butchered topos theory, I butchered SDG, I'm going to butcher generativity, and then like, you know, mix the butchering. So I'm sorry for specialists again, but basically like you start from differential, like smooth manifold in GR and Riemannian metric, actually, which actually is not Riemannian but semi-Riemannian or like pseudo-Riemannian, which means that it's like locally, sorry, infinitesimally, like it can be diagonalized, and the structure of the diagonal is like this. Like you really think of it like tensor 4×4, and you know, like for quantum mechanical people, just -1, +1, +1, +1, and the bases are tangent spaces. So or like cotangent because it's dual. So anyways, and then you impose the condition that you work with Levi-Civita connection for like. There is like neat thing about that. Oh, the structure can be started just from connection and tetrad fields and sort of Palatini action derivation, but I will not go into it. This might not be clear why, but there are reasons to speak about connections. And then you have like Einstein equations, just a PDE. Okay, nice. So the thing is that like there is an additional claim in GR that points on manifolds don't make any, they are like not observable, they don't have any meaning, and so on, which goes like into like a lot of philosophical papers dedicated to so-called Hall argument. But essentially the thing is that like if you have like the value of metric associated to this point, or value of any field associated to point X, and you say, oh, this is X, it actually doesn't mean anything, because like anyone comes and like just does any diffeomorphism. It's actually like reparametrization of the coordinate system on the point, just gives you another coordinate system, and you don't know, like your neighbor is like just even not behind Mars, is just like the other side of the black hole or something. So it's pretty the other side of at least outer horizon. So like, you know, it's kind of pretty damn. So the thing is that, okay, so what we can do it with this is an open problem, what are observables in GR. Like there's, I'm saying this in like covariant, completely covariant formulation, in a sense that's like Lagrangian perspective on PDEs. I'm not saying Hamiltonian. Hamiltonian formulation is not, it's not like generic thing for GR and for those equations. So like it's other story. But like for like totally 4-dimensional GR manifolds, it's an open question. And basically like it's clear that like choosing particular system of coordinates that corresponds to choosing a particular observer. Actually, this observer has also to fix like this Lorentz gauge in each point, but it's another story. Like globally, it's just necessary of fixing coordinate system. And now, what's up? And there are like many solutions proposed. Like none of them really won the game. Nice was really by Bregman and Komar, who just said, oh, like we have metric tensor. There is some other tensor that is like pretty nicely invariant, which is Weyl tensor. It's constructed from derivatives of basically derivatives of Riemannian metric. And we can take those tensors, trace them out, and basically we get like in each point of the manifold, we have like four values that are always different from each other. And they can be used as this like objective coordinate system that, you know, like forget diffeomorphism. However, it doesn't work whenever there's like a symmetry on the spacetime. So like, you know, whatever, like think of Schwarzschild, I could have like a circle and tube and it's a symmetry, and you just don't have it any longer. So this is a trouble. And another thing that is often proposed as like a tentative solution, or like at least tool used for calculations also, yeah, because it's actually a technical question, how you derive the values of your predictions, how you define your predictions. Like observability is like fundamental thing for any physical theory. This or other way around. So it's basically to say, okay, we have some global fields, like 4 scalar fields, and every point, it's kind of those fields are such that like for each point, we can uniquely determine it by the value of those fields. This field is sometimes called DAS. It's kind of dependent on the properties. The thing is that you won't like it to be not influencing the rest of the behavior of the Einstein equation. So like there is some sort of tension in the theory, but this is a sort of thing that has been discussed by many people. Okay, and now with all this stuff, let's pack it up. Okay, so the idea to do GR in SDG was presented by Goods and was developed by him and some people. Actually, there should be GUC because it's Russian and it's Goods, like ts is just Russian ts. But he kind of posted papers on arXiv with TS. So, anyways, and he and some students developed this thing, and they kind of asked the questions and tried to see, for example, like what would be the actual set theoretic shape of the solutions of GR when represented using SDG inside topos and when evaluated at different stages. Yeah, because like there is the stage dependency and like, oh, sorry, I have not told you like one thing about topos theory that's like here fundamental. So basically, like the essential thing is that like if this like underlying category, when you like Yoneda it in, there is a question like what is the global shift? And basically global shift corresponds to a terminal object. This is like fundamental thing. Like and like in those C infinity models, I actually wrote it here, but like I have not told you this verbally, and I promise that you can just ignore everything else, or like mostly. So like if you take like this sort of like single point, it's kind of a bit like non-interesting like C infinity ring, but nevertheless you can do it. And if you take, well, actually like as a C infinity ring, like outside, it's like you use it by this stage. So like you, but anyways, if you take like the global section of the shift, you just get like the standard thing with no dependency on the stages. It's like how to explain it otherwise. Basically, you know, like if you think of like just shifts over topological spaces, no topos theory involved, you might have like shifts are just some sort of like local sections of the bundle, and there's like the question is like of existence or non-existence of the global section of the shift, yeah. And basically, like in topos theory is precisely the same, and in some cases there is no global section of the shift. For example, like I will actually hopefully tell about this later, like the first development in like serious development in applying topos theory to quantum mechanics was actually like proving that Cohen-Specker theory is, the theorem is equivalent to non-existence of a global section. But okay, so basically like an interpretation that I have like sort of suggested like many years ago is that one can think of this stage dependence as sort of generalization of this observability. So like it's so somehow like the way like you generally have like fields and like in standard GR, you kind of have to take care that they are not interacting with the rest of solution of Einstein equations. Here you just like inject it as like an observability thing from the outside. And then you can always move to like global stage and like all this, it's like God's view on universe. It's like, there's like no inner dependence in the point. So, but there's another story. There's like, oh sorry, it's like, so like this is like GR in SDG. It's not only way that one could try to do reconnect like topos theory with GR. There's another way, and there's something very nice. So like there is like in '72, Geroch has proposed the to use again the spectral perspective on manifold that like okay we have like this smooth ring of smooth functions over the manifold. So like let's shift to like smooth rings of smooth functions, but let's generalize it, not take it smooth ring. Let's just be commutative ring, and like let's structurally define metric and connection and like Einstein equations just like on the module of derivations. You can do it at least formally, and then like consider that you can represent it like as C infinity rings in a special case, but in principle, this theory might have like different representations, and Geroch gave no. And the nice thing is that Professor Michał Heller actually presented the alternative representation, like that used so-called Sikorsky representation that and showed that it allows to have like a generalization of GR that includes singularity points and boundary points of the manifolds. Like in GR, when you have like various like if you like study Penrose-Carter diagrams, or like when you have like infinite curvature and you have like singularity in like black holes or something, like those points, actually they don't belong to smooth manifold structure. So they actually don't belong to GR, but like you principally would like to study them from the perspective of maybe some sort of like extended GR. So like this was the motivation, and he actually showed that like some using this Geroch algebra representation with partially kind of, I would say, like mediated by continuous functions in some sense. I don't want to go into details of it, but like one can actually like cover some singularity points. And then he also proposed like to consider not just like those Sikorsky representation of Geroch algebras, Gerosh, I think, Gerosh, people say Gerosh. Gerosh algebras, but actually consider shifts of those Einstein algebras over a space. So you see, it's almost topos theoretic. It just requires like little things to be done. And this was investigated by him and Sachin, and this has led to like this non-commutative work later. But like kind of, I look at it and I thought, oh, well, there is something missing here, yeah. And basically, you can just take the category of Einstein algebras with homomorphisms of algebras that preserve the metric by means of pullbacks, and then do pre-shifts over it and study Grothendieck topologies that make it. It's kind of the very natural thing. So basically, like I think that like such toposes deserve to be called Heller toposes. It's because like the basic Heller's. But it was like in your 92 paper that you presented the idea. I would gladly. Then I will gladly update the terminology. It's honorable anyways. But anyways, the thing is here, and again, like all this kind of issues about like observability and things out there are applicable here. Like in this case, it's like it's to be studied. You know, it's kind of it's delicate, but at least there is some sort of nice framework alternative to models of SDG in toposes, like topos theoretic framework to study also GR directly. So it's kind of okay. So we are done with toposes for a bit and differential geometry and like all this classical stuff. And now I invite you to a tour de force through quantum information geometry. Yeah, let me think how I use forcing in like the models of talk giving. Maybe okay. So I will start from this. So basically, like at the beginning of probability theory, and also statistical inference in the sense, there was like a little tension. So like in the correspondence between Fermat and Pascal, they kind of discuss probability as being founded on probabilities and like finite things and so on, but probabilities. And Huygens, who actually like published his first published book on probability ever in like mankind or something, or at least like modern European probability. He actually used expectations. And well, like in finite dimensional case, it's equivalent. It's also equivalent in measured theoretic context, because like you can start from theory of integral, following like integrals like as basically linear maps on Banach lattices. Like there's like ordered Banach lattices, but this is like equivalent to measure theoretic formulation. It's also equivalent to measures on Boolean algebras as abstract algebras. However, okay, and this is like integration thing. It's nice. Okay, so like in quantum theory, there is like things that are like a bit similar, a bit different. So there is a notion of a state that like usually when people discuss like sort of basic elementary things in quantum theory, they start from like pure states, which are vector or Hilbert space, but like it's just like a beginning story, like the like true states of like quantum mechanics. In even finite dimensional are like density matrices. I mean, and the density matrix is like it's like positive if you like normalized density. It's like a trace class operator, You don't need to go really into understanding this, because anyways, I will say in a moment something that subsumes it both. But like just generally like to write, because I want to like have this as a like object for statistical inference. So like, okay, so like if you take measure spaces, like for example, probabilistic models are some sort of things that you cut off in L1 space. You can think of it basically as like spaces of Radon-Nikodym derivatives or something. And like Gaussian models are like densities of measures with respect to like dominated measuring or something. And very similar things, like basically like whatever you want to do with probabilities, and like not only basically, but like very abstractly also, you can do with density matrices. It's just think that trace is like integral, and density matrix is like probability density, and like everything goes. Okay, but the thing is that like, okay, like why we should have two formalism, and like, okay, so what is the minimal conjunction of both? And this is given by the notion of W-star algebras. It's like Banach theory thing. It's like pretty abstract. It's, if you know like sister algebras, commutative or not, like for example from Gelfand representation, basically W-star algebra is a sister algebra that is dual to some Banach space. That's all. It's kind of super abstract. But the nice thing is like it gives immediately like in two special cases you restore O measure theory, and I really mean O, and also all quantum mechanics in this Hilbert space framework, like this. So so like if you ask, okay, what would be the nice quantum states to be considered? Yeah, you'll probably start from like spaces of subsets of preduals of W-star algebras. And the nice thing is now that actually you can do most of things that are the structural elements of integration theory for like over measure spaces or over Boolean algebras and so on. You can do all of them, or like almost all of them, because some things are just not provable in non-commutative case. But basically, like all structure, like LP spaces, like conditional expectations, like basically anything that like Radon-Nikodym derivatives and so on, it's a pretty hardcore thing. Like you need to like relative modular operators to do the work and so on. It's like, you know, it's like a lot of functional analysis behind it. But at the end of the day, if you just want to use some algebraic letters and like be happy that theorems are out there, yes, they are out there, which is great. Which means that actually like this is those states, those candidates for like calling them like states are actually integrals. You actually have like spaces of integrals, which is great. And the next thing is that like there is no measure theory that corresponds to these integrals that would be equivalent, which is very fundamental. Okay, and now the next thing is that like using W-star algebras is fundamental beyond just pure quantum mechanics. If you want to have such things like mathematically exact Unruh effect or like Hawking radiation, you need to use like KMS and use modular operator to prove basically both results. So it's kind of it's not only mathematical generalization, it is, but it's also like it's absolutely like necessary for if you want to have like mathematically exact predictions. So now I will come to, so we have in the background this non-commutative integration theory, this non-equivalent to measure theory. And now there are like two things that are troublesome. So one thing is the failure of quantum logic, which is like one of the favorite Bob's things that happen. Like you usually refer to it in various papers that quantum logic was nice. Oh, yeah. Quantum logic was nice, yeah. But basically like in 80, like quantum logic was nice, but first of all they hoped for having like integrate like quantum measure theory, and it's not there. I mean, general enough. You cannot have like all those results. So you need to have to have W-star algebras if you want to have like generalization. And the other thing, you don't have tensor products, and the project is dead. Yeah, precisely. Oh, you're actually on the next paper that I'm saying that. Oh. Tensor product and Bob, but wait. So okay, so like there is no goal for tensor products. There is like no goal from non-commutative integration theory. And actually, like I would say that this what I'm doing is sort of like the other side, taking the other side like in a way like this Bob is doing sort of is like taking seriously tensor product, and I'm kind of taking seriously non-commutative integration, trying to go that direction. Like if you want to have like some sort of like distinction of what is happening there, and I would definitely be shorting it. So, but the other thing is also very interesting that also this idea of spectral paradigm gets, you know, like this, you take algebra, this commutative, you have a spectrum, it's a space, and you kind of switch between them, kind of, it is, I'm sorry to like bring bad message, but it's sort of dead, because there is no non-commutative generalization of spectral theory. Like from the perspective of non-commutative integration, like estimation of expectations is more fundamental, and projections are just like, I mean, you can use them in calculations, and they are very relevant for calculations, but they have no status for like, fundamental status for a theory. And then also like if you consider seriously some insights from like convex operational approach, and definitely I don't have time to like really combine it with all of this, but basically like with POVMs, kind of, you also no longer believe in fundamentality of projections, and dually for quantum logic of measures on projections or lattices of projections. So like the sort of spectrality, either like Gelfand style with commutative algebras or like von Neumann-Stone style with projection operators and quantum logics, is kind of, it's a no-go. So I just want to like have like last feature of topos theory. So like, or maybe I will not. Maybe I will just say very briefly. So like, okay, if it's that, maybe you can do hating algebras and try to somehow like inject toposes into, like inject like quantum theory into toposes, and this was like this project of like topos theoretic thing developed by Chris Isham, and in a way like you can prove some things like Cohen-Specker being non-equivalent, like non-existence of this global Schiff functory. It's kind of, it's nice, you can prove something, but the trouble is that you cannot like prove everything what you would like to do, and like whatever you do in like finite dimensional Hilbert space is kind of, you really like, you know, teleportation, like blah, like those things. It's kind of the inner logic of topos is Cartesian closed, but like it's not monoidal. So I mean, it's like monoidal Cartesian, but it's like quantum tensors are non-Cartesian monoidal. So the thing is that, like for example, like in Cartesian categories you have cloning and like what corresponds to like physical. Maybe you were saying about this, maybe I'm just losing the time to say. But basically like there are like things like that, one things in physics of that like are direct consequences of non-Cartesianity of tensor product, and it's also like sort of, if you want this quantum theory in topos to be not just like somehow patchwork it, that some things are like working, but if you would like to have canonical categorical structure, you have to sort of face that those tensor products have to somehow be there. So, bam, okay. So, yeah, still. So like I'm almost there where I wanted to be. Don't judge me based on the number of slides. You know, like the art of life is to renormalize hopes up to your resources, or maybe something else, but it's a nice statement. Okay, anyways, so basically like, okay, I was telling you about what could be the best thing for what are the objects of, like I'm trying to build up some categorical setup. Yeah, and I told you objects would be like some sets of those non-commutative integrals which happen to be states on W-star algebras. Okay, but now what are the morphisms? Yeah, and now like just to get back to commutative probability theory, there was Bayes Laplace, then there was like anti-Bayesian frequentist things that were nasty things that were happening in the 19th century. Then Kolmogorov came with the conditional expectations, and then it was quickly generalized to Markovian maps, which is basically positive normalized linear maps between spaces, probabilistic spaces, like L1 spaces, if you think. And then like in quantum theory, it was like kind of paralleled, just the time scale was compressed. So like von Neumann and later corrected by Luders proposed like this projective measurement rule, which is, it's kind of, there are like projections involved like those. And then like conditional expectations were, quantum conditional expectations were introduced like post-war, and then was quickly Steinspring with like CP maps that became the sort of like since then they are kind of paradigm of standard quantum information theory. But the thing is that like all those maps are actually like, because you already are working with like the states of, that can be taught as states of knowledge, you know, like just probabilities, just generalized ones, yeah? kind of, you can think of those maps really not like a sort of like ontic dynamics, but basically like inductive inference. So like coming back to like the original intuition, is something what you would do vertically. Sorry, horizontally. I kind of forgot where is horizon. So like horizontally. And now there's nice things for like also not only historical reasons, but like the first explicit introduction of category theory to statistical inference, at least published, because Lavier was in '62, but like the published one and definitely independent of Lavier, was like the papers in Chensov and Morsak-Steller, where they independently presented the, say, okay, like let's consider the category where we have like spaces of probability distributions, densities, measures as objects, and those Markovian morphisms as maps. So like for Chensov, explicitly, it was a part of like large program, and that he was like basically from the second paper he was explicitly committed to, and it was, and basically it has to put in the context, and this is like where information geometry comes in. Basically, there was like discovery that's very important quantity in statistical estimation called Fisher information metrics can be actually seen as Riemannian metric on the space of probabilities. And then Chensov was the first person who like really extended this framework geometrically, and he introduced affine connection. In a footnote, he thanks his wife for the idea. And then, like in next paper, which is called Categories of Mathematical Statistics, it's all in Russian, but some translations are out there. He presents this there, and he makes a reference, like explicit reference to Klein program. And I will go with this on the next slide. And like as a reference for category theory, he actually does it. There is no it seems that he doesn't even know about this. There is no MacLean-Eilenberg. There is Godeman, which also I think it's intriguing because it shows like this algebraic geometric aspect and shift theoretic. Okay, and there then he introduced like few things. In particular, he characterized the Riemannian metrics and affine connections that are monotone, which means like not increasing in well-defined sense, uniquely defined sense, under the morphisms of a category. So he started to use like categorical structure for characterization of the behavior of spaces of integrals, or like spaces of probabilities. And this program was carried on to quantum case, and the similar characterizations were obtained. But here is like something that I would like to quote, because somehow this is the very characteristic also about his self-awareness. In his monography, he says that when he says system of all statistical decision rules, he means basically like Markovian morphisms. It's like terminology of Wald, so like it's like specific terminology. But basically, he says that like families of probability distributions play the roles of figures, and decision laws like Markovian morphisms play the describe movements. And it's kind of very explicit, like Kleinian / categorical view. And okay, so now there is like a dense info of a twist to Chensov program that can be done, and which is some sort of like thing that I've been involved. So basically, in Chensov approach, and basically in all of this, what is like standard probabilistic and quantum setup, you have those positive and completely positive linear maps as a fundament. And this is linear. You also have tensor products between like linear spaces. Kind of, it's a neat framework altogether. You have like the linear world, and it works. However, there are like some limitations to the notion of CP map. For example, like in algebraic approach to quantum field theory, like it's like very fundamental result that if you start from a state that is global, like overall Minkowski spacetime, and you ask, okay, like so, like what the localized observer in some like local region sees, it actually like you know that you will get a state that is not only mixed, but generically it would be entangled state. So basically, like somehow, like in like when you just go out of the like standard like problems of quantum mechanics, like when you consider like basic framework, really basic framework for like fields over space-time, and it goes for predictive quantum theory and field theory. Yeah, like you immediately don't have like this tensorial separability. And the thing is that then you cannot like really use CP maps as a fundamental object, like in general. It doesn't, I mean, in situations where people apply those, it applies, but like generally it's clear that it's insufficient. Okay, so this is like something, okay, so this poses a question, okay, so if not CP, then what? What should be the basic morphisms? And now there is a nice thing that like people started to derive a bunch of results showing that various updating rules, Bayesian, like Bayes Laplace, but other results also conditional expectations, can be derived from, in probabilistic case, not quantum, can be derived from constrained maximization of relative entropy. I will explain you in a moment what does it mean, but basically it's some sort of morphism, nonlinear morphism when constraining entropy gives you the map. And recently, like basically it was kind of my research with friends and my master student, there was like a result that both von Neumann-Lüders rule and also partial trace, which amounts to basically everything what you have in CP maps that is not tensor product and not unitary evolution. And unitary evolution is some sort of like, it's a bit non-inferential aspect of quantum theory. For example, it doesn't exist in Jordan algebras. So, but it doesn't matter right now. The thing is that like, basically like whatever is inferential in CP maps, it actually is, can be derived from constrained relative entropy maximization. So somehow like this suggests that those maps can be a replacement of this underlying morphisms. And okay, so this is one thing. Another thing is that like all those like, it has been shown that like those metrics and connections on probabilities and also quantum probabilistic spaces and quantum state spaces can be derived from Taylor expansion of relative entropy. So actually relative entropy not only generates you the morphisms that are like nonlinear and like provides some alternative to CP maps, but also it gives you like local differential geometry whenever it's available, whenever you actually have a smooth manifold. And the nice thing is that like when you look on the classes of what type of families of relative entropy are out there and so on, there are those that are like characterized by monotonicity with respect to Markovian morphisms, and sort of it will give you Markovian morphisms still in the background. But there's another class, so-called Bregman relative entropies, that basically don't require you to presume anything in the background, and they are characterized by the one thing that I have not told you about, which is like the generalized Pythagorean theorem, which is the following. Okay, so there's like quantum equations. So like 3 slides or 4, and I'm done. Quick slides. So this is like explanation what is actually like entropy maximization. You take entropy, like let's say absolute entropy, like Shannon entropy, von Neumann entropy, and you take some constraints and you pick up the state that maximizes this entropy given that constraint. So you kind of choose the state that is like the best, the maximal, something that is like satisfy the constraints, so like it encodes your data, but it's maximally non-committal, like maximally uninformative, like if entropy is like negative of information, that like max end is like minimum of information about anything else. So, and then if your constraints have some parameters, like temperature is like a parameter for like, like thermodynamic states, like, then you have a family of states. Yeah. So this is how you can generate a state space. And the same you just do for morphisms. The thing is that you have already some state space generated this other way around. You take a state, you put your constraints, which is something that you learn, like the new data, like this what you put in Bayes theorem, or like this what you actually put in like CP instruments as like data for them. And then you just like maximize entropy constraints. Really? Sure. Oh, really? Okay, then this is like entropic updating. So like let me close this with finding the slide that might make sense. Okay, this is what I was telling. Blah blah blah. Okay, this is So basically, you can do a category of those. Oh no, 43 is okay. I think that the nice slide is basically here, somewhere here. Okay, okay, Bob, like you are my master right now. So like, let's do it like this. So basically, the thing is that I just don't know which of those slides is the best. But let's take this one. I just explained you how to construct models from entropy and how to do morphisms with relative entropy maximization. Okay. So now the thing is that like all this process can be promoted to a functor from like the category of data to like category of like state spaces and morphisms. And the nice thing is that all of this can be put in like adjoint, like doing Clavier inverse. So like just taking that like the adjoint factors are going like in the opposite direction, because Clavier proposal is for deductive systems of inference. And the main point is that like for deductive systems, like the geometry adjointness thing is the opposite. So like basically the claim, and the nice thing is that all of this is an example of like general framework for like adjointness for inductive inference. And another example is like the framework developed by the Rio Kramer-Renner. It's like a special case. Yeah, and that's all. Yeah. Yeah, it was nice.